Jam, in this video, you are literally going to build a tokenized real-world asset. And to do so, we're going to buy some Tesla stock, use actual Tesla stock as collateral for a token that we're going to mint on the blockchain. Now, of course, we're going to use a paper trading account, but you're literally going to go through the exact steps on how to build something like this. What are tokenized RWAs? Tokenized RWAs, or tokenized real-world assets, are assets in the meat space, real world, that are turned into tokens. And doing that connection from the real world to a tokenized asset can be very difficult, but it's much easier with Chainlink. And that's what we're going to build today. And we have a GitHub repo that I've created that shows you two of what I think are going to be the most popular ways to build these tokenized RWAs. One of them is already quite popular in this industry, and that is the synthetic asset with on-chain collateral. You see this in a lot of popular stablecoins, like, for example, DAI or Liquidity stablecoin. Then additionally, we're going to be doing the second most popular type of tokenized RWA, and some of these already exist today, the backed asset, or the fully reserved. This is when your collateral is off-chain and it is fully backed. There is a centralized component to doing this system. However, we're going to reduce the centrality as much as possible, of course, using Chainlink Functions. This type of tokenized real-world asset already also exists today with popular stablecoins like USDT or USDC, where the dollars are stored in a bank account somewhere, and there's a centralized entity that says, hey, we'll exchange the tokens for dollars at any time. And we're going to show you probably what I think are going to be two of the most popular setups. The first one is using Chainlink price feeds to create the synthetic asset. You can also use Chainlink functions if you have enough data sources. And the second type of tokenized RWAs is where we have actually purchased some real world asset like a stock. It's custodied somewhere. And then we use Chainlink functions to actually govern our smart contract and govern where those real world assets go. And so we have a token that can always reflect the price of the assets that we've purchased. I made a video about all of this at the high level, so you should definitely go check out the description to watch that video. However, we will do a quick recap of what we're building and the different types of assets, etc., in this video before we get going. And in this video, we're just going to go over the backed asset, the fully reserved asset with off-chain collateral. Why? Well, the one with on-chain collateral, the synthetic one, you've probably already done if you've gone through Cypher and Updraft. And if you haven't gone through Cypher and Updraft, you 100,000 million% should. We go through a Foundry stablecoin where we build essentially a tokenized real-world asset with our own stablecoin. Because yes, stablecoins are tokenized RWAs. And we're not going to go through the synthetic model because if you've gone through Cypher and Updraft, you've essentially already done it. There's only a little bit of tweaks that you need to do to adjust it for a Tesla stock or something like that. However, all the code for this will be available in the GitHub repo that we're going to go over in this video. So before we actually get cracking on this for real though, I want to show you what the final project is going to look like. So this is the GitHub repo to this. Link will be in the description. This is the Patrick Alpha C RWA creator GitHub repo. And if we scroll down in here, you can see there's a README. You can read more about what this is and what it's doing. And there's a nice little picture here that we're going to go over real quick. So we're going to be building these two types of tokenized assets. Or we're going to be building one of these two, but in the repo, both of these are there. So, and the synthetic one, the one that we're going to go over right now, is really easy to build if you've already gone through the stablecoin tutorial. The first one is going to be a synthetic asset where the collateral is stored on chain, where you have some type of pool that's on chain and you have different types of collateral. Like in here, I have Ethereum stored in a smart contract on chain. Now, what happens is once you store this collateral in here, you store 1 ETH of collateral. The pool uses a Chainlink Oracle, a Chainlink price feed to give you the price of the token, for example, the Tesla stock. And it says, okay, you put 1 ETH worth of collateral in, I'm going to give you 1 Tesla token. And then at any time you can go back, redeposit the Tesla token or burn the Tesla token back to the pool and get the ETH collateral back out according to the price of the Tesla token. So for example, if you put in $1,000 worth of ETH, maybe you get 5 Tesla tokens back. And then if the price of Tesla skyrockets and ETH doesn't move, maybe later on you put 1 Tesla token back in the pool and you get your ETH back and you get both, 1 ETH and 4 Tesla tokens or something like that, right? Or maybe that's a bad example, but hopefully you get the picture. This setup is actually the exact same setup as the Foundry DeFi stablecoin that we go over in the Cypher and Updraft curriculum. If you want to learn more about how to build stablecoins, definitely be sure to go through the Cypher and Updraft curriculum. We also have video of it on my YouTube as well. But essentially, a synthetic asset, a synthetic tokenized real-world asset is going to follow the exact same setup as that stablecoin tutorial, The difference is instead of minting a dollar pegged coin, you're going to mint a Tesla pegged coin or a Apple pegged coin or a Microsoft pegged coin or an Amazon pegged coin, or etc. We're going to be using Chainlink price feeds to do this. However, if there is no Chainlink price feeds, this is where Chainlink functions could come in and be the replacement until a proper Chainlink price feeds is available. And don't worry, we're going to be going over Chainlink functions as well. Hold your horses. Because now what I think is the cooler or more novel use case that I really want people to build is this one, the backed asset or the fully reserved asset. So now instead of users depositing their Ethan, they actually just buy Tesla stock and maybe they put it in a bank. In our case, we're going to be buying Tesla stock on a brokerage called Alpaca. And you do the exact same thing. Once you have Tesla in your bank account, there's a smart contract that's reading the price of the bank account. Once again, using a Chainlink Functions oracle. Once it sees that there's stuff in here, it will actually mint the Tesla token. The idea is there's a centralized intermediary where you can always return your Tesla token for the price of the actual Tesla stock or for the actual Tesla stock underneath. And the Chainlink oracle is going to be the one that governs this system. So both of these systems, both of these tokenized Tesla tokens are going to be tokenized real world assets. However, the approach is very, very different. On the left side, we're using a synthetic asset, and it's called a synthetic asset because the token itself isn't collateralized by actual Tesla tokens. It's collateralized by other stuff that equals the value of one Tesla token. And on the right side, this one is truly collateralized by actual Tesla tokens. So one Tesla is actually backed by one Tesla. However, there is a bit of a centralized intermediary in here. So these two approaches have the different trade-offs. The synthetic asset is arguably much more decentralized. However, it's not actually backed by a Tesla. The backed assets are actually backed by Tesla. However, they are more centralized. And in this repo, if we scroll down to the SRC, this is where our code bases are. We're going to be going over building D Tesla. And to me, this is the more interesting one of them. The D stands for directly backed Tesla. So this is going to actually involve us buying Tesla stock, holding it in a custody, and using that Tesla stock to collateralize minting our tokens. Additionally, in here, we have some notes with CCIP on building your own tokenized bridge, because what's a tokenized real world asset? If it cannot go cross-chain, it's kind of not that helpful. So that's in here too. We're not going to go over this in this video, but I highly recommend you try out CCIP because it is really freaking cool. Without further ado, let's go ahead and get started building our dTesla.sol. And this is the one that has literally unlimited customization. So if you want to build something completely novel in Web3, this is the approach that you should take, because nobody's building with this yet. And it's like blowing my mind that nobody's building with this yet. But like you can build so many cool things that don't exist yet with this setup. So take this, go make something amazing, and then tweet at me when you become a billionaire. And then also come to Siphon for a security review. And of course, this code base is just for demo purposes only. Use it to inspire you, but maybe we'll make it a first flight on CodeHawks, who knows? And as a PSA, never test your smart contracts on a testnet. Always do it locally first. I'm doing it on a testnet here just for the video. Always do locally first though. All right, so let's go ahead, let's get started. So I'm in my VS Code here. I'm in my RWA creator folder. If you wanted to, you could also just git clone this repo and run the test and play with it as you want, but let's show you how to build it from scratch so that you know what you're looking for and what you're thinking about while you build this, because there's actually a lot involved. Let's start writing down the README, what our architecture is going to look like so that we know what's going on. So here's going to be our setup here. So only the owner of our smart contract is going to be able to mint the dTesla token. Anyone can redeem their dTesla token for USDC or the stablecoin of choice. So this is actually what's going to keep the dTesla token pegged. You can always sell or swap your dTesla token for USDC. And this is a really cool novel functionality that we actually don't see for a system like this. Right now, for example, with USDC on chain, you can't, the Circle stablecoin doesn't allow you to swap it for a different stablecoin of choice. Once you call this redeem, Chainlink Functions will kick off a Tesla sell for the USDC, then send the tokens that were sold, the USDC tokens, literally send them to the contract. So this Chainlink Functions is literally going to send our smart contract USDC, which is insane, after selling Tesla tokens. And then finally, the user will have to call finish redeem for them to pull their USDC out. So this is what we're going to be building for this first one. Let's go ahead. Let's get started. So of course, we're going to forge init. Forge init -- force. Boom. We have everything set up. Let's go ahead and delete these. And let's create our dtesla.sol. And let's get started coding. Pragma. I'm using GitHub Copilot to do a lot of this coding for me. And you'll see me hitting tab a lot to do so. So you know the drill. Contract dtesla. Like so. Maybe some nat spec if you like. Say what you want to do about it, etc. So let's go in here and let's start defining some of our functions. So the main one is going to be function send mint request, right? And what's this going to do? This is going to be external. This is going to be the function that where we send an HTTP request to do the following. Number one, see how much Tesla is bought. And then number two, if enough Tesla is in the bank account, we're going to mint dTesla. I'm going to say alpaca account. So that's what this one's going to do. So this is going to be our minting function. This is going to be a 2 transaction function. And this can be a little bit confusing for new devs, but basically this is going to be a request and receive. So we're going to send a mint request. Our Chainlink Oracle is going to read that. It's going to go check our bank account or our alpaca account. It's going to go see if there's enough Tesla in there. And then in a second transaction, it's going to call back to our contract and say, hey, yes, you have bought enough Tesla, or no, you don't have enough Tesla bought. You can't mint any more D tokens, or excuse me, you can't mint any more D Tesla tokens. So since we have this send mint request function, we're also going to need to have a function underscore mint fulfill request. And this is going to be internal. And I'll show you why in a minute or two. So we're going to send a mint request. Chainlink node is going to do some stuff, and then it's going to give our answer back to this function. And like I said, I'll show you why it's internal in a minute. Okay, then what else? Okay, so we need to additionally have a function send redeem request. And this is the cool superpower of this smart contract and how this is going to be really, truly a tokenized Tesla token. So this is going to we'll do at notice. User sends a request to sell Tesla for USDC, or our redemption token. For our use case, it's going to just be USDC. This will have the Chainlink function call our alpaca, our bank, and do the following. Sell Tesla. It's going to sell the actual Tesla token, buy USDC on the brokerage. So this is actually all going to happen on the brokerage or the bank account, and then send USDC to this contract for the user to withdraw. So Chainlink Functions is going to facilitate all of our off-chain stuff, which is why the smart contract is so freaking cool. And same as what's up here. This is a mint and fulfill. This is going to be a redeem request and fulfill redeem. So this is a mint request, mint fulfill, redeem request, redeem fulfill, right? Because we're doing this off-chain stuff and we need a Chainlink Oracle to govern all that for us. So we're going to do a function redeem fulfill request. This is also going to be internal, and I'll show you why in a minute. We're going to need some other stuff in here as well. We're going to need some other functions, of course. But at the end of the day, these are kind of the major functions that makes this whole thing work. So let's go ahead and start building this bad Larry. So let's work on this send mint request. And there's going to be a lot of stuff just in this one, because we're going to be working on Chainlink functions, Chainlink this, Chainlink that, Chainlink the other thing. So be sure to smash the like button, hit the subscribe button. Let me know in the comments if you're enjoying yourself so far. And take a deep breath because we're about to dive in. So somebody wants to mint some Tesla, right? This is the function that they're going to call. Let's have our parameter be uint256 amount. So they're going to specify the amount that they want to mint. I come to this contract and I go, hey, I would like 10 D Tesla tokens, please, right? So for now, we're only going to have this be an only owner modifier. And the reason for this is we don't want there to be some people trying to do some hairy stuff with a bank account while there's requests in flies with this, that, the other thing. So we're going to kind of just lock this down. And to lock this down, we're actually going to use confirmed owner from the Chainlink repo, because we're going to be using a lot of Chainlink stuff. And we're going to have to go ahead and forge install Chainlink. So now normally I could just forge install directly from the smart contract kit Chainlink repo. However, there's way too much extra code that I don't want to install. So I'm going to install the Chainlink Brownie contracts, which is much nicer. We're going to install 0.8.0. So we're going to do forge install smart contract kit / Chainlink Brownie contracts at 0.8.0 -- no - commit. Should spell contracts correctly. Lovely. And now we're going to go in our founder.toml. We're going to add a little bit of a remappings equals at Chainlink / contracts equals lib / Chainlink Brownie contracts / contracts like this. And now we can do at import this confirmed owner at Chainlink / contracts / src / v 0.8 / functions / dev / v, oops, excuse me, shared / access / confirmed owner.sol, like so. And now we'll say our dTesla is confirmed owner. So confirmed owner is basically a nicer implementation of the only owner from OpenZeppelin. And I like it a lot because of that. And then in our, and since we're confirmed owner, we need to have a constructor of confirmed owner of message.sender. Like that, cool. We even do a little forge build just to make sure, but it looks like we're good to go. So now we can have this only owner modifier on send mint request. And then if you're following along with the repo, we also have this when not paused. It's probably a good idea to have this contract be pausable. Since this is going to be a bit of a centralized contract anyways, having this when not pause is going to help a lot when it comes to minting and redeeming these tokens from a security perspective. And additionally, if you're following along in the repo, I added some of options like this where we actually will revert if it thinks there might not be enough collateral. But for now, we're just going to skip that because this is only owner and we're just going to assume our owner is very intelligent and never really messes this up. So if that was confusing to you though, don't worry about it. But basically what we're going to do is in here is we're going to set up a Chainlink Functions. Now, if you've never worked with Chainlink Functions, you should head over to docs.chain.link. Scroll down to functions. There's a lot of wonderful resources in here. If you go through the documentation, definitely recommend you going through one of the guides, one of the getting started tutorials here before you actually work with this, because there's a lot of stuff to do. However, at the same time, we're going to set you up. So, and if you go to the docs in here, go to getting started, you can scroll down in here, scroll down. This is actually probably the best tutorial for you to go through. Scroll down, scroll down, scroll down. Where's my code base? There's a big button. Here we go. Big button to remix. This actually gives you one of the basic setups for working with Chainlink Functions. And I'm going to copy paste some of the code in here. So first off, we need to make our contract a functions client. So I'm actually just going to copy this instead of writing this all out myself. This functions client code base. Let me do a little comma here. And we're going to get rid of this at sign. It's actually we're going to get rid of that at sign, and then it's also in functions/dev, I believe. Okay, cool. Confirm owner functions client. And if we command click on this, this functions client has a lot of the internal functions for actually sending requests and working with the Chainlink Oracle. So functions client, confirmed owner. And of course, it's getting mad at us because we're not using the functions client constructor. So we'll do functions client. And for the functions client to work, we need something called the functions router contract. So back in the Chainlink documentation, whenever we send a function, whenever we call this send mint request, we actually need to route this call to a specific smart contract on the blockchain that we're working with. So if we go to supported networks in here, we see the different supported networks for Chainlink Functions at the moment. For now, I'm going to hard code this to Sepolia. But if you look at the repo that we made here, the functions router is actually dynamic and you can change it depending on what network you're working on. And if you go to like the scripts, for example, where we actually deploy it, same thing, it actually gets the router from a config file that we set. But for now, we're just going to hard code it. So at the top, I'm going to say address Sepolia functions router equals, and then paste it in here. Address constant. And now it's also saying dTesla should be marked abstract right now. And that's because if we look in here, we scroll down, we need to define this function fulfill request. And this is going to be the callback function that the Chainlink Oracle responds to. I'll explain that in a minute, don't worry. So we're getting set up here. So we have send mint request, external only owner. We now have our contract being a functions client. So we can actually send and work with the Chainlink Functions bit. What's next? Well, if you go through the Chainlink documentation, this is some of the boilerplate for actually sending a request here. And I'm going to make this a lot easier and more readable for us to go through though. So what we want to do is we're going to make an object called a functions request memory object called REQ or request. So back in the documentation, there's this functions request library. I'm going to copy paste it. Delete some stuff. I'm going to delete this here. We're also going to do /dev like this. I think that's right. Maybe that's not right. Got to get rid of this at here. There we go. This functions request, if we command click, this is a library for actually creating this request object. And this is what we're actually going to be sending to the Chainlink node. If I toggle the word wrap on, this is what's so cool about Chainlink Functions is you can actually send arbitrary code to these functions. And it's this arbitrary code that we're going to use to call the Chainlink Functions, have it actually buy and sell and send USDC, Tesla, etc. This is what the object looks like. It's going to have the code location of the source code that will be executed on the dawn. Secrets location. This is any like API keys or secrets that we need. Coding language. Right now, JavaScript's only supported. Boo. But it's okay. This is actually the raw JavaScript that we're going to write. So this is going to be the raw JavaScript that's going to execute on the Chainlink node itself. And we're going to store this in our smart contract. So we have some encrypted secrets references. This is encrypted URLs for the secrets locations, any arguments that we want to pass to the source code, and then any bytes arguments that want to be passed to the source code. So we can essentially pass anything that we want. So anytime we make a call to a Chainlink Functions object, we have to pass this rec object to the Chainlink Functions router. And the code that we're going to be writing is actually going to be in JavaScript. So up at the top, up in our constructor, I'm actually going to add this in here. So I'm going to say string memory mint source code. Now let me toggle the word wrap. And in our constructor, we're going to create a little string. Well, we would create a mutable, but string memories don't work as a mutable in Solidity yet. So we're going to do string private s_mint source code. So we're just going to stick it in storage. Say s source code equals mint source code. And anytime we call our Chainlink Functions, we're going to use this mint source code. And don't worry, yes, we are going to write this source code, which is going to be a lot of fun here. So since we're going to be writing in JavaScript, down here, there's a function called initialize request for inline JavaScript s_mint source code. This is basically going to tell our rec object that we're going to be using JavaScript. And since this is a library that we're going to use on this object, up at the top, in order for us to get access to this function, we of course need to do using functions request for functions request dot request. And that's going to give us access to this function here. Next, we're going to say request ID equals underscore send request. And this is a function that comes with the functions client. And it takes a bytes object, subscription ID, callback, gas limit, and a dawn ID. So we can put most of that in here. So the data is actually just going to be this request object. So we'll do req.encode CBOR. And this encoding function just encodes a request to CBOR encoded bytes, which is concise binary object representation, which is a way that Chainlink nodes understand data. Next, we're going to need to give it a subscription ID. So the subscription ID is going to be our ID. So anytime we work with or pay, anytime we make a call to a Chainlink Functions, we have to pay a little bit of either Chainlink token or native gas token, and that's governed by our subscription ID. So also in our constructor, we're going to do a uint64 sub ID, and this one can be immutable. So we'll do uint256 immutable I underscore sub ID, and we'll say sub ID equals sub ID, I sub ID equals sub ID, and we're going to use this immutable sub ID. Next, we need the callback gas limit. This is something I'm just going to hard code at the top. We're going to do uint256 constant gas limit equals 300,000. Don't worry about setting this for now. Just go through the docs and you'll learn more. You'll learn a little bit more about setting an appropriate gas limit. And then finally, the DON ID. So once again, in the Chainlink documentation, there's the DON ID. This is going to tell our functions router which DON or which Chainlink decentralized Oracle network to send our call to. So we're going to say, we're actually going to hard code this as well at the top, but again, in the repo, it will be dynamic. So this is a bytes 32. So we'll do bytes 32 constant DON ID equals, and paste it in like this. And just to make absolutely sure it's hex, we'll set it up like this, just to make absolutely sure it is a bytes object and not a string for some reason. Boom. And request ID is going to be a bytes 32 request ID. And the subscription ID should be a uint64. Sorry, let's fix that. Good. And gas limit should be a uint32. So this is going to send a request. We haven't written our source code for the request yet, but we will. Don't worry. And great, at the end of the day, this is all we need to send our mint request. Obviously, we're going to define the source code, but in the fulfill request, we actually want to map. We actually want to make sure we're working with the correct request. So we're going to do a little bit of a mapping so that we know what's being requested with what different send. That might not make sense, but it will in a minute. So I'm actually going to create a struct, a new type, to store all the data of our mint request sendings. So I'm going to do a little new struct type or struct d Tesla request. And in here, we're going to have the uint256 amount of token, address requester, and then mint or redeem. So I'm also going to make a new enum, mint or redeem, where it's either mint or redeem. So we're going to save this dTesla request as an object in a mapping. So I'm going to create a new mapping of bytes 32 request ID mapped to dTesla request private s underscore request ID to request like this. And in here, we're just going to do that mapping. So we're going to say s underscore request ID to request of the request ID equals a new dTesla request. My GitHub Copilot got it. Amount message.sender mint to redeem.mint. Boom. And that's essentially it. And then, oh yeah, returns bytes 32, return request ID. Okay, cool. Mint request done. Next. Well, what's going to happen? It's going to say, oh, how much Tesla's bought. If enough Tesla's in the account, we're going to mint. What the heck? Weird. Okay. If there's enough in the account, we're going to mint some dTesla. So whenever a Chainlink Oracle calls back to a contract, it's not going to call back to mint fulfill. It's not going to call back to redeem fulfill. It's always going to call back to just plain old fulfill. So we're going to have this function. And if you remember in the functions client, right in here, it has this fulfill request. This is what we need to define. Otherwise, our contract will never compile, and that's good. So we're going to have our function fulfill request, and this is going to take a bytes 32 request ID, bytes memory response. And then if there's an error, we would put an error here too, but I'm just going to say bytes memory. We're going to ignore any errors for now. This is really helpful. Obviously, if you're making like a customized Chainlink Functions bit, you can say, hey, if there's an error, put on chain what the error was. And this is going to be an internal override like this. Now, why is this internal? Well, because the Chainlink node is actually going to call handle Oracle fulfillment, and handle Oracle fulfillment is actually going to call fulfill request, which is what we're going to define right now. So it needs to be internal. So now when we send both our mint and our redemption request, both of them are going to get called back to this fulfill request function. When working with Chainlink functions, it doesn't matter if we call mint to our Chainlink Oracle. It doesn't matter if we call mint. It doesn't matter if we call redeem. The Chainlink Oracle is always going to respond with fulfill request. It's always going to go through this fulfill request function. So if we call mint or if we call redeem, this function is the entry point for it to call back, right? So we say, hey, can you mint us some Chainlink tokens? Chainlink goes, yeah, sure. I'm going to call fulfill request to do that. We go, hey, can you redeem us some tokens? Chainlink's going to go, yeah, sure. I'm going to call fulfill request to do that. So we have to do a little conditional in here. We'll say if our s_request ID. So since it passes back the request ID and the response, of course, the request ID to request of the request ID dot mint or redeem. And this is why we did this before, equals, what did I say? Mint or redeem, mint or redeem. There we go. Equals mint or redeem dot mint. Then we're going to call the mint fulfill request. Otherwise, we're going to call the redeem fill request. Thank you, GitHub Copilot, for filling that in for me. So cool. So it's going to call back to fulfill request. And then this is going to route it over to our mint since we are minting. So how does this work now? Let's pretend here that our smart contract just assumes that we're going to have enough collateral. Like I said, in the actual project in here, there's a couple of additional checks it has. I would argue it probably needs even more checks, but it's fine if the owner messes it up, then the owner messes it up, you know, it's an only owner function. Anyways, so remember our Chainlink function is going to check how much Tesla is bought, and then it's going to return with what we're going to do. We're going to return the amount of Tesla value in USD is stored in our brokerage. So we're going to actually be checking how much Tesla we've bought. And then if we have enough Tesla token, mint the D Tesla. So in here, we're going to say, okay, well, the UNT 256 amount of tokens to mint is going to be equal to, oh, yep, it even got it for us, s request ID, request ID dot amount of token. Oh, and then we need to pass the bytes 32 request ID and also the bytes memory response. So let's do that in here as well. Request ID response down here as well. And then we'll have the redeem look the same. Okay, cool. So we're going to get the amount of tokens. Now we have to do something a little bit tricky, right? So we want to say, okay, in this response, in this bytes object, our Chainlink node will have responded with either yes, you have enough, or no, you don't have enough. So we need to take this response, decode it from bytes to a UNT 256, and save that as a portfolio balance. So at the top, we're actually going to make a new storage variable, UNT 256 private s_portfolio balance, like this. And we're going to say s portfolio balance equals UNT 256 bytes 32 of the response. So we're going to cast our response to a bytes 32 and then a UNT 256, and we're going to save it. And then what we're going to do is we're going to say, okay, if the Tesla collateral value, aka how much Tesla we've bought, is greater than the D Tesla to mint, then mint the token. So we need to convert. So this means we need to figure out, okay, how much Tesla in dollars do we have? And then how much Tesla in dollars are we minting? So we actually need a way to get the price of Tesla. And this is where not only are we going to use Chainlink functions, but we're also going to use Chainlink price feeds as well. Now we could 100% just use Chainlink functions to get the pricing, but the Chainlink price feeds is going to be much more reliable, obviously because it's way more decentralized and probably way better than anything we're ever going to be able to do with functions. So we're going to need to basically say, okay, if the collateral ratio adjusted total balance of the new amount of tokens to mint is greater than the portfolio, then we're going to need to revert, D Tesla not enough collateral. I know this function is defined, neither is this error. Let's go ahead and add those. Boom. So this is going to be a pretty intense function. So get collateral ratio adjusted total balance. I know this is kind of weird, but trust me, it's going to make sense. Basically, we're going to say, okay, the amount of tokens to mint plus all the total tokens, all of the value of all the tokens should be less than the total portfolio value. We always want to have more money worth of Tesla stock than money worth of Tesla tokens. And again, if this is a bit confusing, definitely be sure to go through the Foundry DeFi stablecoin course on Cypher and Updraft because it's the exact same setup. So we're going to make this new function called get collateral ratio adjusted total balance. And in here, we're going to have it take a UN256 amount of tokens to mint. It's going to be an internal view. It's going to return a UN256. And what we're going to do in here is we're going to say UN256 calculated new total value. If this is a little bit confusing, don't worry. I promise it'll make sense in a second. Get calculated new total value amount of tokens to mint like this. And we're going to create another function. Get calculated new total value. Actually, GitHub Copilot pretty much has me, except for that function is kind of wrong. Get calculated new total value, where this is going to be the new expected total value in USD of all the D Tesla tokens combined. So we're going to return, we're going to say total supply, and we don't have this function, so we're going to have to add it, plus added, let's do added number of tokens, add number of tokens, times get TSLA price, which we haven't defined it either. We're going to define this in a second, divided by precision, which we haven't defined either. We're going to define this, all of this in a second. So there's a lot of stuff going on here. So basically we're going to say, okay, if there are 10 tokens already, 10 Tesla, D Tesla tokens, and there's going to be plus 5 more D Tesla tokens, that's going to be 15 Tesla tokens, multiply that by the D or the Tesla price, let's say is $100, it's going to equal to 1,500. So there should be at least $1,500 in the bank account in our custodian, right? And then we have to do this divided by precision because you know how Solidity math works. So at the top, we're going to create some more constants. We'll say a little math constants. UN256 constant precision equals 1E18 divided by precision. We don't have total supply because we're not an ERC20 token yet. So we're going to need to make our D Tesla and ERC20. We're going to grab this from OpenZeppelin, from @OpenZeppelin. I think that looks right. Because we're doing this, we're going to have to install it. Forge install OpenZeppelin / OpenZeppelin -contracts -- -no -commit. And while that's installing in our foundry.toml it looks like GitHub Copilot got it for me, @OpenZeppelin contracts, lib OpenZeppelin contracts, like that. Great. Okay, great. Cool. So now we have total supply function. Now we need this get Tesla price. We're going to create this down here, get Tesla price. We'll make this a public view, and I promise in the GitHub repo, the functions are cleaned up a little bit nicer. We'll say returns a uint 256. And this, we're going to get the Chainlink price in here. So we're going to do import. And if you're unfamiliar with Chainlink price feeds, shame on you. You should definitely go watch Cypher and Updraft. We're going to get this from, if you follow along with the repo, we actually have this Oracle. If you're following along with the repo in here, we actually have this libraries folder where we're using this Oracle lib, where it does a little bit of staleness checks. I'm not going to go through that for now. I'm actually just going to copy this for now and just grab directly from here. However, I do recommend using some type of Oracle library whenever you're working with Chainlink price feeds. Get Tesla price. We're going to say aggregator v3 interface price feed equals, and this is where in our constructor, normally we would pass the Tesla price feed in here, but I'm just going to go ahead and hard code it in here. So if we go to docs.chain.link, overview, data feeds, feed addresses, price feed addresses, scroll down. We're going to go to Sepolia testnet. Now for fee address, price feed addresses, we would have to pick a network that actually has the Tesla price feed. So for now, we're actually just going to go, we're going to go with Polygon because I think Polygon has the Tesla. If I search Tesla in here, yep, Polygon has the Tesla price feed. But for this demo, we're just going to work with Sepolia because Sepolia is a little easier to work with. And we're going to say the link USD price feed is going to be the Tesla price feed. So we're pretending Link and Tesla have the exact same price. So we'll say address constant Sepolia Tesla price feed equals this. And just say this is actually Link USD for demo purposes. Anyways, aggregator v3 price feed equals aggregator v3 price feed, Sepolia Tesla price feed, and GitHub Copilot actually got most of my stuff correct here. We're going to say price feed.latest round data, get the price, ignore most of the other stuff in there. And then we're going to say returns price, returns uint256 price. Now, the Tesla USD price feed, if we go back to Polygon, go to Tesla, show more details, has 8 decimals, and we want everything to have 18. So normally you would additionally check for decimals. However, I'm just going to hard code this as 10 decimals. We're going to call this additional feed precision. uint256 constant additional feed precision equals 1E10, like this. And we're going to say times this so that we have 18 decimals, like this. And then we're going to return instead. What are we mad about? No arguments past the base instructor. Oh, yeah, we probably should do that. So let's do ERC20, D Tesla, comma, D Tesla. Okay, a whole bunch of stuff just happened here. Let's finish up. So get Tesla price, get calculated total new value. So we're going to get the price. We're going to times the price by the total number of D tokens. And then we're going to take this calculated new value, multiply it by some collateral ratio, and then divide it by collateral precision. And we're going to return it. So what are collateral ratio and collateral precision? I can't even speak. Well, we're going to have a uint256 constant collateral ratio equals 200. And what this means is we need a 200% collateral ratio, which means if there is $200 of Tesla in the brokerage, we can mint at most $100 of D Tesla. We always want to be over collateralized. We never want to have we never want everything to be backed 1-to-1. We'd rather one D Tesla token have at least 2 in the bank, just in case there's some crazy price volatility with Tesla, which there's a good chance there might be. So we say, okay, grab this calculated new value, grab this calculated new total value, times it by the collateral ratio, and then divide it by collateral precision, because since we're doing multiplication and this is Web3, we also need to do uint256. We also need to do uint256 constant collateral precision, collateral precision. Since we are multiplying by 200, we then, of course, need to divide by 100, right? So, and this is equivalent to being like 2/1 or, twice. We need twice as much collateral, right? Because Solidity and fixed math is hard in Solidity. We have to do this weird math stuff. Cool. So all of this, why do we do all of this? Well, in the mint fulfill request, we basically want to say, hey, do we have enough Tesla purchased in our brokerage to mint more stuff? And if not, we should not mint. So that is what we're checking here. We could also, instead of revert, we could optionally let it go through and just say, hey, completed, but we're not going to mint anything. But in our example here, we're just going to revert. But if there is enough money, then we'll say, okay, well then if the amount of tokens to mint does not equal 0, which I would hope it's on 0, we're going to go ahead and mint the amount of tokens to mint to the s_request ID to request ID dot requester, comma, amount of tokens to mint. Ta-da. All right, so that's pretty much everything we need for the mint function. So this whole process will mint us the D-Tesla token. And don't worry, I'm going to show the whole backend with the alpaca and actually buying the Tesla and selling and all that good stuff. So we're just going to finish the smart contracts first. Again, if you go to the GitHub repo, we actually have some real-ish tests, but be sure to hit like and subscribe, keep watching because, oh, it's about to get so much sicker. All right, let's keep going. So now that we've minted this stuff, let's actually build the system that's going to keep the price pegged, right? It's this redemption that's actually what's going to keep the Tesla token price pegged. So the owner of this contract is going to mint these tokens, right? And they're going to sell them. They're going to put them on like a Uniswap. They're going to become like a Uniswap liquidity provider. They're going to get LP fees for doing that. Maybe they sell it directly, whatever they want to do. Once they sell it to people, people can then redeem them at any time for the actual value of the underlying tokens. Obviously, the owner of this brokerage is taking a lot of risk here. The owner of this brokerage isn't taking really any risk. If they actually have the Tesla in their bank account, then if the price 10x's, well then whatever, it doesn't really matter because they have the Tesla and they can always sell the Tesla to fulfill these redemption requests. And this is where this actually becomes really, really cool too, because all you'd have to do to turn this into a profitable business is you just add a little fee switch to the redemption process and boom, now you're making money for providing the service. But excuse me. Anyways, so send redeem request. Anyways, so send redeem request. So this is where someone takes their Tesla token and they say, hey, I want to turn this in for its dollar equivalence, now. So in the same thing, this is a request and redeem setup. It's going to be 2 transactions. We're going to send the request, say, hey, can you sell the Tesla? Send the USDC. And then in the redeem fulfill request, all the tokens will have been sent to this contract and the redemption will be fulfilled. So in send redeem here, we're going to do the same thing. We're going to say, okay, how much UN256 amount D Tesla, how much D Tesla do they want to send back? So in the first thing we want to do is we're going to create a minimum redemption amount. Why? Well, because some brokerages have certain amounts that are a minimum requirement. So for Alpaca, which is the brokerage that we're actually going to use here, for USDC, there's a 20 USDC minimum here with a fixed withdrawal fee as well. So we're just going to bump this up to 100 just because we're going to be a little extra safe in case Alpaca decides to rug us. So we're going to say UN256 constant minimum withdrawal amount equals 1E6, excuse me, 100 E6 because USDC has 6 decimals because it's a weirdo token. Normally we would say like 100 E6 because USDC is a weirdo token, but we're going to keep everything in 18 decimals. So we're going to do 100 E18 like this. And then we're going to come back down and we're going to say, okay, if the amount of Tesla is less than our minimum withdrawal amount of 100, then revert. Or we could also let this go through and give them a refund. That's probably the better way because that's probably the better way to do this. But in any case, so we're going to say UN256 amount Tesla in USDC equals, and we have the get Tesla price, but we're also going to have a get USDC value of USD function or get USD value of USD and a get USD value of Tesla amount Tesla. So first we got to convert this Tesla amount to USD, and then we have to convert the USD to USDC. Now you might be asking, oh wait, wouldn't USDC just be equal to USD? And you might be right, but the price of USDC is actually not always one-to-one, right? So let's actually, let's go to Polygon mainnet. Let's go look at the USDC USD contract, right? Let's go take a quick look at this. We'll go to the contract, read contract. Let's look at, where is it? Latest answer, latest round data down here, query. You can actually see the price is not quite one-to-one, right? It's really, really close. It's almost one-to-one, but the price of USDC actually fluctuates a little bit based off of supply and demand, but it's mainly pegged to one, but we want to just get the most accurate function that we can get. So once again, we're going to have to do a little bit of mathage. So first off, we're going to need a function. So in addition to getting the Tesla price, we're going to need to do a function get USDC price. This will be a public view, returns. This actually will be exactly the same as this, 256. And instead of Sepolia Tesla price feed, we're going to do address constant USDC, or Sepolia USDC price feed equals. Let's go back to Ethereum. Let's go down to Sepolia. There should be a USDC, USD. Boom. We're going to grab this, paste it in here. And we're going to say get USD price feed, Sepolia USDC price feed. We're going to do the same thing, return it. That looks pretty good to me. And then we're going to create this function get USDC value of USD, UN256 USD amount, public view returns UN256, return USD amount times get USDC price divided by precision, because these are going to have 18 decimals. So we're going to do that. And then we're going to do function get value of TSLA, UN256 amount, or Tesla amount, public view returns UN256 returns like this, return Tesla amount times get Tesla price divided by precision. This. So get USDC value of USD. Oh, what do I have? Get USDC value of USD. Cool. So now we're going to get the amount of Tesla in USD. So let's say I want to redeem one D Tesla token. We're going to say, okay, well, one D Tesla token is worth X USDC. And then we're going to say if the amount of USDC is less than the minimum withdrawal amount, we're going to revert with a custom error. We'll say error. This should have 2 underscores, not just 1. Error D Tesla doesn't meet minimum withdrawal amount. Boom. Doesn't mean minimum withdrawal amount. And then we're going to put another underscore up here. Cool. Now, same as before, when we send a request, we're going to need to initialize it and send it. So let's go ahead. I'm just going to copy these 4 lines, bring them back down to here. We're obviously going to change this a little bit. So instead of the mint source code, this is going to be some redemption source code. So in our constructor, mint source code, sub ID, we're going to have string memory redeem source code like this. We're going to say s underscore redeem source code equals redeem source code. And we're going to put this right underneath here, copy paste, redeem source code like this for our storage variables. Nice. Headers, state, storage variables. Nice. And we're going to do one more. Headers, functions. These are constants and immutable, so they're technically not storage variables. Cool. Anyways, we're going to do s underscore redeem source code, like so. Send request. encode it, sub ID, gas limit, dawn, request, that looks good. S request ID to request ID equals dTesla amount to request, amount dTesla, message sender, mint to redeem dot redeem. Now for this source code, we're actually gonna mix it up a little bit. I'm gonna put in this string array memory args equals new string array 2. And the reason we're gonna do this is because we need to, for the redemption, we need to tell our brokerage how much how much Tesla to sell for USDC. So we need to send this as a parameter to whatever script we write here. So we're gonna say args 0 is gonna be equal to amount dTesla dot string. We need to stringify everything. So to get this toString function, we're going to import a library called strings from OpenZeppelin contract utils strings.sol, and we'll say using strings for uint256 like this. And then back down here, now we can do amount dTesla.toString. And then we're also going to pass args1 amount Tesla in USDC.toString. So we're basically going to tell our brokerage, sell this much Tesla and send this much USDC back to the contract for the user to get. And then we're going to do rec.setArgs to args, like this. Then we're going to send the request. And finally, we're also going to call burn on the message.sender and the amount dTesla. So in order for them to get the USDC value of their dTesla, they have to actually burn the dTesla here. So they're going to burn their dTesla, send this request, and then it's going to get fulfilled. Now, because they're not going to have their tokens here, technically we should have some type of refund mechanic in our redemption. We're not going to add that. That's a future improvement for you to add here, but it should be fairly trivial for you to add. So finally, so this is going to send the request, hey, I want to redeem 10 Tesla for USDC. We're going to sell the Tesla on our brokerage. We're going to sell the Tesla. Then we're going to send the USDC to this contract and allow them to withdraw it. Once the brokerage sells the Tesla and sends the USDC back to this contract, we're going to need to redeem it here. So we're going to have this redeem function where we're going to say, okay, we're going to have the response be the uint256 USDC amount equals uint256 bytes 32 response uint256 USDC amount WAD. And again, if you're following along with the GitHub repo associated with this, we do some clever stuff where your redemption token doesn't technically need to be USDC. It could be really any token, but we're going to set this up as if we're assuming it's only going to work with USDC. So the actual code base looks a little bit different. When we work with our API and when we work with Alpaca, we're just going to set everything to be 18 decimals. So we're not going to really mess with this, although we would mess with this decimals bit here. So we're just going to say, okay, this has, assume for now, this has 18 decimals. You know, this would be definitely a security vulnerability in a contest here. But now we're going to say, okay, if our API returns 0 equals 0, then we're going to say uint256 amount of the Tesla burned equals s underscore request ID to request ID dot amount of token. We're actually going to do kind of a refund here. We're going to mint them back their original amount to request ID dot requester comma amount of burned, and then we're just going to return. So if we send them nothing, if we didn't send them anything, we're going to say, okay, just give them their money back. All good, no sweat. Otherwise, if we did send them the money back, we're going to say, okay, great, s underscore user to withdrawal amount of s underscore request ID to request of request ID dot requester plus equals USDC amount, like this. And we're going to put in a mapping way at the top in storage. We'll say mapping address user to U256 pending withdrawal amount, private s underscore user to amount, user to withdrawal amount. And then we probably want to emit an event here and stuff. And then finally, we'll do a little function here. Finally, they can actually withdraw external. So UN256 amount to withdraw equals s underscore user to withdrawal amount message.sender s underscore user to withdrawal amount message.sender equals 0. We'll set it to 0. And then finally, we'll do ERC20 of USDC. So let's just hard code that on this here. So we'll say address constant Sepolia USDC equals. For this token, I'm going to use this hard-coded token that I just created. It's not verified or anything, but this is the contract. It's got this mint function, so we can play with it. So we're going to take this contract address and we're going to stick it in here. Now we have a fake Sepolia USDC token that we're going to be using. And now way at the bottom, we can finally do, okay, this dot transfer message dot sender, comma amount to withdraw. And do this little transfer here. And since we're not using safe lib, we'll do a quick bool success. If not success, revert with the Tesla transfer failed. Error. Like this. Okay. So that is going to be our redemption. So we're going to send a redeem request. Say, hey, I would like to swap out this D Tesla for USDC, please. On the back end, we're going to sell the Tesla, buy USDC, send the USDC to the contract, which is going to call this function here, put it into this mapping, and allow them to withdraw that amount of USDC from our contract. Very exciting. Very, very exciting. Let's just add a couple of view functions at the bottom. There's view and pure, just so that we can have a couple of getters in case we need them. So we'll do a quick function get request, be a bytes32 request ID, public view returns D Tesla request memory. Oh, this is where GitHub Copilot is really good. Get pending withdrawal amount. Thank you, GitHub Copilot. Get portfolio balance. Perfect. What else? Get sub ID. Sure. Mint source code. Sure. Redeem source code. Sure. Collateral ratio. Sure. Collateral precision. Sure. And I don't want any more. That's more than plenty. Okay. Cool. So this is looking pretty fantastic. But this is just the tip of the iceberg, my friends. We're just getting started. But now, if you're still watching us, if you're still with us here, congratulations. There's a lot more to go. Now might be a great time to get some coffee or some ice cream. Gear on up, smack the face, because we're about to write the script to actually govern the Chainlink functions and actually do all the backend stuff to really make this a tokenized real world asset for Tesla. So get excited. Let's jump in. So now that we have all of that set up, we can actually go back. We can actually now start finally writing the code to actually govern the brokerage stuff, right? Because right now, all we have is a smart contract, right? In our smart contract, when we call send mint request, this is not going to do anything, right? Nothing is going to happen here because when we send this request, we don't have any source code, right? Like when we deploy this, we need to say what the mint source code is and what the redeem source code is. We have neither one of those. So let's go ahead and let's actually get started working with Chainlink Functions. Now, again, it's great if you've been through the Chainlink Functions tutorial, but if you have not, no worries. We are going to get you set up and get you squared away. So if this is your first time working with Chainlink Functions, phenomenal. No sweat. So if we go to getting started with Chainlink Functions, we've already gone through most of our stuff. The Chainlink Functions has a functions playground where you can actually write some code in here and test it out right in here, which is great. But we can also test it out, everything out right in our VS Code or in whatever coding setup that we're working with here. So what I'm going to do is I'm actually going to create a new folder called Functions. And this is where we're going to create all of our functions stuff. Now to do this, you do need some JavaScript, right? You do need NPM, you do need Node, etc. So if you've never worked with JavaScript before, guess what? Now's the time to learn it because Functions really only supports JavaScript at the moment. I told them to support Python, don't worry. But so to work with Chainlink Functions, we're actually gonna install this Chainlink Functions toolkit. So this is actually a JavaScript package that's gonna help us simulate and help us run and work with Chainlink Functions. Now you do need a couple things. You need Node.js 18 or higher and Dino 1.36 or higher. The reason you need Dino is because that's gonna be the server that we're going to use to pretend to send our requests. And it's how we're going to simulate being a Chainlink node, and then we're actually going to, do the whole thing. So Dino -- version, we see something like this. Node -- version, great. npm -- version. So we're going to want to install this, and I'm going to copy this right here. And this is going to set up like a package.json and everything for us. And yes, we're going to be working with some npm stuff. So this is where the JavaScript starts. I'm sorry for the people who are not JavaScript pros. So we're going to do npm I @ chainlink/functions toolkit. And this is going to help us, like I said, simulate all the API calls that we want to make. Because the first thing that we want to do is right in here, again, is we want to do this mint source code, right? Yes, add.getIgnore, add node modules to .getIgnore. Absolutely, always do that. So, and you can go through the docs here if you want. I think it'll be a little bit easier if you just follow along with me though. So we have our functions folder, and inside of our functions folder, we're gonna make 3 more folders, okay? We're gonna do new folder, configs, new folder, configs, another new folder, simulators, and then another folder called sources. So as this is installing here, configs is where we're gonna have all of our configurations. Sources, this is going to be the meat of what we're working with here. This is actually what we're going to stick on chain. Simulators and configs, these are just things to help us run our simulators and help us test locally that our source code is actually working correctly. So let's actually get started writing the main source code first, then we'll set up the config in the simulator to run our source code, and then we'll actually do it. So this is going to be really exciting because we're now going to shift into working with Alpaca to actually do all of this stuff, right? So first thing that we're going to do is we're going to need to go to Alpaca API brokerage, Alpaca developer first trading. You've even got some like notes in here on how to work with Alpaca. So we're going to come to the app.alpaca.markets and we're going to go ahead and sign up in here. That'd be 0 knowledge, password and stuff. Once we're verified, we can now log in. And now we're logged into app.alpaca.markets and we're on a paper trading account. And this is what we want. So we're going to set up a fake brokerage account to actually pretend to do this. Now, if you want to do this for real, obviously you would just switch this over from a paper trading account to a real trading account and then do the, real trading. So we're just going to do this as Alpaca trading though. So what we're going to do is we're going to select, we're going to be an individual. Next. We could do all this stuff, but I'm not going to because we're in a paper trading account and I can do whatever I want in a paper trading account. So in our fake little paper trading account, we start with $100,000. And what we would want to do, I think the stock market's closed now. So as of recording, it's actually past 4 p.m. So the stock market's closed. So none of my buys will go through, but that's fine. What we can do is we can still scroll down in here. I can look up Tesla. Looks like the market price is $177 right now. I'll do a market order. I'll say I want to buy, I don't know, maybe 200 shares or 1,000 shares, which would be this much money. We'll do a good till cancel order, review the order, confirm order, and boom, we've now placed an order. So since the market's closed, we're not actually going to be able to buy it, but that's fine because we're only going to pull the portfolio balance anyways. So a little bit cheeky here. We probably would update our script just to read the amount of Tesla instead of the portfolio balance, but I digress. It's all good. So now that we have our Alpaca set up, what we can do is we can actually go to the documentation for Alpaca to actually learn how to make these API calls to this system. And for working with the API, we're gonna want to go to home and then scroll down and API keys, generate new keys, and boom. I'm gonna leave these up here because I don't really care if you steal my fake little dummy keys. And so in a notorious .env file, .env, we're gonna do alpaca API key equals here, alpaca secret key equals, and we'll place it here. Now, as you know, you should never, ever, ever do something like this in production, but since these are dummy keys, this is fine to use. But obviously, as you know, never, ever, ever put real API keys in a .env file unless you're asking to be owned. Same thing with private keys, right? You never want to do this. Why? Because, well, if you turn this into a real account, these API keys will have access to buy and sell random and we don't want that. So cool. So now that we have that, we can actually make with the documentation. So if we go to API, it'll open up the documentation here. We can actually make our API call to check our balance in here, which is going to be 100 grand, or we probably should have it check how much Tesla we have, but that's fine. We're just going to check the balance here. Okay. So what we're going to do is we're going to come in here. We're going to go to API reference and we're going to zoom in just a hair, zoom out just a hair too. And we're going to look for, we're going to go to accounts, get account, and this is going to be the API call that we're going to make. So it gives us a couple different ways to actually run this, but I'm just going to go ahead and run it myself. But if you want to learn more about the docs in Alpaca, you can just rip through here, shell, node, whatever you want to use. So in here, what I'm going to do is I'm going to go up to functions, sources, we're going to create a new file. We'll call it alpaca balance.js. And yes, we have to write this in JavaScript, but it's okay. We're not going to be upset about it. And when we run this in the Chainlink environment, it's actually going to inject a whole bunch of objects into this JavaScript script for us. And one of the first ones is going to be secrets. So we are going to tell our config, in our config, that this Alpaca balance comes with some API keys, right? So we're going to say if secrets.alpaca equals blank, or secrets, or secrets.alpaca secret equals nothing. Then we're going to throw an error, say need alpaca keys, like this. And in fact, the Chainlink documentation has a section in the API use secrets using Don hosted secrets. There's even a section where it'll help you encrypt your passwords, encrypt your secrets locally so that you can actually send them to a Don. And when we actually have our secrets, when we use these API keys from our Alpaca account, there's a couple of different ways we can actually store them. One of them is actually to encrypt them and use something called threshold signatures, where we will upload them to a Dawn, a decentralized Oracle network, in a way where any one Oracle can't decrypt it. And we'll actually upload them to a gateway with our secrets. And that's how we're going to work with our API calls. The encrypted secrets will never be put on chain, and that's good. We don't want them ever put on chain. But we'll do that in a little bit. We're not going to do this quite yet. So we're going to check for these secrets. And like I said, we're going to upload these to the Dawn. Our secrets are not going to be stored on chain, but we want to actually now write the rest of our function. So we're going to make a call to our Alpaca account and get the portfolio balance. Like I said, a better version of this would be to get the total amount of Tesla, but this is a little bit easier for the demo, so I digress. Anyways, const alpaca request equals functions.make HTTP request. You can also use fetch in here as well. So we'll say the URL is going to be this base URL right here. HTTPS paper Obviously in the real Alpaca account, you're not going to have this paper bit here. Headers are going to be accept application/JSON, the APCA API key ID, right? So APCA API key ID and the APCA API secret key are going to be secrets.alpaca key, and the APCA API secret key secrets.alpaca secret, like this. And then what we're going to do is we're going to run this request. So this just builds it. So we're going to say const response equals await promise.all alpaca request. And if we had more requests, we could put them in this list here. Then from this response, we're going to say const portfolio balance equals response.data.portfolio value console.log alpaca portfolio balance $$ portfolio balance, like this. And then this portfolio balance is going to be this, $100,000. Now we have to encode this value to be put on the blockchain. So then we'll just say return functions.encode uint 256 math.round folio balance times 100. And this is it. This is our script. We're basically just making a call to our account, checking how much value is in there. Like I said, for this to be a little bit better, we would check how much Tesla is in there, but this is great. However, we want to simulate what this is actually going to look like when we send it to a Chainlink node. So we're going to create a new simulator called alpaca mint simulator.js. And this is what we're going to use to actually test sending this request for what it's going to look like on chain. So now that we have our script up, we need a way to actually simulate this script so we can test this locally, right? This is simply a GET request, right? We're basically just getting, hey, get us the balance of our account. So we're going to want to go ahead and simulate this. And we're going to build a little simulator right here. So let's go ahead and do this. So first, we're going to do a little async function main, make an async function. And then at the bottom, we're going to do main.catch error function console.error process.exit code equals 1. Basically, when we run this, it's just going to run our main function, which is this one right here. And if it has an error, it's going to print it out here. So this is like some JavaScript-y stuff to work with these async functions. And this is all we're really going to do is we're going to run this alpaca balance function, but we're going to actually import this simulate script and this decode result from the @chainlink/functions toolkit. Oops, like this. And in here, we're going to do await simulate script, and we're going to simulate our alpaca balance. However, I kind of cheated a little bit here. The thing that we're going to simulate is this alpaca balance script, but in order to run our simulate script function, which if we command click into it, this is from that Chainlink package that we just imported, we actually have to pass a config, which is what we're going to do now. So let's now create a config called the alpaca mint config.js. And this is going to be the config that we're going to use to run our simulator. So the Chainlink docs do a pretty good job of fleshing out what needs to be in here, but we'll do a little const fs equals require fs. This is so we can read files. We'll do const location return type code language. You'll see why we need these in a second. Language equals require @chainlink/functions toolkit. Request config equals source fs.read file sync /functions/sources. What do we name this? alpacabalance.js /alpacabalance.js. And this is going to be the source file. Then we're going to need a code location, which is going to be location.inline. We're basically saying location. And this is saying where the code is going to be found, which is just going to be in this file, or when we actually run it, it's going to be literally in our smart contract. Secrets. We're going to have to upload our secrets to the Dawn, and we'll show you how to do this in a second, but the secrets are alpaca key, which is going to be process.env.alpaca key, and then alpaca secret, which is process.env.alpaca secret. Or what do we say? Alpaca secret key, alpaca API key. Okay, so let's do that. Alpaca API key, alpaca secret key. Secrets, location, location.don hosted. Args is going to be no args, we're just getting the balance here. Code language, it's going to be code language, that is written in JavaScript. And then expected return type is going to be return type.uint256 because we're returning a uint256 balance onto our code base. Then we'll do module.exports equals request config like this. And boom, this is our mint config. And now we're going to import that into our simulator here. So const request config equals require .configs/alpaca mint config.js. And we're going to pass this request config to our simulate script, which again, this comes from the Chainlink Functions toolkit package. And this is going to return an object that we're going to deconstruct here into response bytes hex string, error string, and captured terminal output, error string. And then we're going to say, if we do have this response bytes hex string, then we'll do console.log response returned by script. And we're just going to pass in here the decode result response bytes hex string, comma, request config dot expected return type. So we're going to decode our result with this decode result again from the Chainlink functions here. And then we'll do, in here we'll do dot to string \n like this. Oops, \n. And so this should give us the balance of our portfolio. And then just below we'll do if error string console.log. Oh, thank you, GitHub Copilot. Error return by script, error string. So I know we just did a whole bunch of stuff. So quick recap of what we did. We wrote our alpaca balance, which is going to call our alpaca account, figure out how much money is in there, or more correctly, it should figure out how much Tesla is in there, but we're just doing money for now. How much Tesla is in there. We wrote a little config here, which tells our simulator how to work with this. And there's a couple of things in here, such as the location.don hosted, where we're going to be uploading our secrets to the decentralized Oracle network. We'll do that in a little bit. And then we have our alpaca mint simulator, which this is actually going to be what's simulating. Oh, and I guess I can just like underscore that. Oh, I guess we'll just do it like that. And this is actually going to simulate what happens on the Chainlink nodes. So let's go to our package.json and we'll create a little script in here. Scripts to actually make it easier to just always run this. So we'll do simulate. This will be source.env. So we're going to want to run source.env and then also node and then our script that we just ran. So source.env and node./functions/simulators/al. What do we call it? Alpaca mint simulator.js. Oops, this needs to be over here. Okay, moment of truth. Let's give this a whirl. So if we pull up our alpaca accounts in here, I'm actually recording. It actually took me a couple days to record this. So our Tesla buy actually went through in the time that I started recording this, and the Tesla stock has gone up. So it looks like we made $500 in a day for buying, a whole bunch of Tesla. So cool. So it should return our balance in our alpaca portfolio. So to run this, we're going to do npm run, since we're going to run this script here, npm run simulate. This is going to reach into our package.json. Request is not defined. Okay, yep. So this should be require. Let's run it again. Missing param, and we're missing a source param here. And this is probably because, yep, I need to export these two. Okay, let's try again. Nope, never mind. So actually, yeah, you do need to export those two. And then doing a console.log of the request config, it looks like the source is this buffer right now. That's not what we want. We're gonna do read file sync dot to string. Let's get rid of that console.log added in here. Now let's give this a whirl. Response returned by script is this right here. If we pull up our alpaca, looks like it just changed. It's probably gonna keep changing. Let's see if we get the up-to-date one. Okay, it keeps changing like every second, so that makes sense. But it looks like we are indeed returning the response here. Excellent. Our simulated Chainlink function is working fantastic. So a quick reminder again of what this all does, right? So we're gonna deploy this. This thing is gonna live on chain. This JavaScript code base is gonna live on chain, not the secrets. This is gonna live on chain. Then what's gonna happen is we're gonna send our secrets up to the Dawn, and we're gonna use this really cool thing called threshold signatures so that even the Dawn, even the different single nodes on the Dawn can't read our secret here. We're gonna send it up to the Dawn so that it can execute our script. And this is a little simulator we just ran here to simulate exactly what the Chainlink nodes are gonna do when they get our script. Phenomenal. Okay, so what do we have to do next? Well, next, of course, we need to upload our secrets to the Dawn. So I'm gonna go ahead and make a new file, not in any of these folders. I'm just gonna create a new file called upload secrets.js. We're gonna make a little script here to do the uploading. And this isn't really super important to learning how to do this. If you wanna just copy mine out of the GitHub repo, you're more than free to do that. But let's go ahead and show you how to do this. So we're gonna do const secrets manager equals require at Chainlink /functions toolkit. And then we're going to do const ethers equals require ethers, like this. So now we're going to create const. We're actually going to do the same setup as over here. Async function, upload secrets. And we're going to do the same little setup here, except for instead of main, we're going to do upload secrets. That looks good to me. And in here, we need a few things. So we need the const router address for the Chainlink Functions router. We can go to the docs here. And actually, right in the using Dawn hosted secrets request, this tutorial here is really helpful for doing this. But we're going to go to functions, read the docs, supported networks here. Pull a testnet, functions router. We're going to copy this, make this a string. Then we need the const Dawn ID. And this is where we're going to use fun Ethereum Sepolio 1 in the docs. This is the Dawn ID for smart contracts. This is for their API endpoint. So Dawn ID equals this. Const gateway URLs. These are the URLs that we're going to upload our secrets to. So we're going to use both of these like this. Then we're going to grab const private key. Don't worry, we're not going to upload this. And I will say, of course, this is a terrible way to do private key stuff, is to stick it in a private env file. However, for this tutorial, I'm going to do this. Since using JavaScript here, there are some easy ways to encrypt your keys so that you get prompted whenever you run this for a password. I'm not going to show you how to do that here because this tutorial is already super long. If you're doing this for production, never, ever, ever, ever do what I'm showing you here. Got it? And actually, it would be the same thing for your alpaca secrets. You would want to encrypt them as well. Then we're going to say const rpc URL equals process.env.sepolia rpc URL. I'm not going to put these in my .env. I'm just going to set them directly in my environment. But you can put these in your .env. Of course, like I said, encrypt this stuff because this is bad practice here. Const secrets equals alpaca key. And so these are the secrets that we're actually going to upload to the Dawn. And if we could go to our mint config, we can actually just copy paste these right here. Copy paste exactly what we're doing in our simulator. And we can do alpaca key process.env alpaca API key, alpaca API secret, like that. And then when we actually upload this, we actually want to go ahead and sign this. So that's why we need this private key. We have to sign it when we send it up, and we have to create a provider. So we're going to do const provider equals new ethers.providers.json RPC provider RPC URL. Then we can do const wallet equals new ethers.wallet private key. Const signer equals wallet.connect provider, like this. Const secrets manager equals new secrets manager. Signer functions router address. This is us actually setting up our secrets manager object, .id. And what we're going to do is we're going to initialize this secrets manager .initialize. Oh, we want to await this as well. This is basically going to set it up, and we're almost there. We're almost home. Const encrypted secrets equals await secrets manager .encrypt secrets. And this is why we did all this stuff up here. So we're using our signer with the functions router and the Dawn to basically encrypt and sign our secrets. And this encrypted secrets is what we're going to upload to the Dawn. If you want to make sure it's encrypted, you can do a little console.log to make sure it's encrypted. For sending this encrypted secrets bunch up to the Dawn, we need something called a slot ID number. This is basically what secret slot that you want to use. So you get each user kind of gets their own slot. We'll say 0. We'll say const expiration time minutes equals 1440. This is going to be a day. So you can set an expiration time on these secrets if you want to have to basically re-authenticate every X number of time. And then finally, const upload result equals await secrets manager .upload encrypted secrets to Dawn, and the encrypted secrets hex string is going to be the encrypted secrets object .encrypted secrets. So encrypted secrets, comma, gateway URLs is going to be those gateway URLs. Slot ID is going to be slot ID number. Minutes until expiration is going to be expiration time minutes. And then if upload result .success, we're going to throw a little error, thanks GitHub Copilot. Otherwise, console.log, checkbox, secrets uploaded successfully, response, upload result. And finally, const Dawn hosted secrets version equals parse int upload result dot version, just so that we know what version we're on. And then console.log secrets version. Okay, I wrote this kind of quick and there's a lot in here, but what we're doing is we're grabbing all the data we need to upload our secrets to the Dawn. So in order for our script, our source here, to be called, we need these two private keys, right? So what are we going to do? Well, we're going to upload them to the Dawn that's actually going to be executing our script. We're going to be uploading them to this group of nodes running Chainlink Functions. However, we want to encrypt these secrets. So we're going to encrypt them in such a way that they're going to use something called threshold signatures, where if enough Chainlink nodes come together and give their private keys, they will decrypt it to run these scripts. So this way they stay secret, but we can still do really cool things with the Chainlink Dawn. So now let's come to our package.json, little comma, upload secrets, make a new script called upload secrets. This will be source.env and node./functions upload secrets.js. Like I said, I already have a couple of things in my environment right now, such as my private key and RPC URL. So I'm just going to go ahead and wing it. So let's do npm run upload secrets. See if this works. Secrets uploaded successfully. Response object. I should fix that. Secrets version. Boom. So our secrets have been uploaded to the Dawn. Very exciting. Sepolia, the Sepolia Dawn now knows what our secrets are. Let's freaking go. Very, very exciting. All right. So all of this was so that when somebody calls send min request, we can send a request, check to see if we have enough Tesla purchased. And if we do, we'll respond with this number, right? Remember how we said portfolio balance equals the response, right? So we're going to get the portfolio balance stored on chain. And if we have enough money, we're going to mint the D Tesla tokens. Fantastic. Now, the next part of this is obviously writing the redeem part. However, I think at this point you have a pretty good understanding of what's going on. And the redeem side is actually really long. There's a lot in the redeem side, and I don't think it's super pressing that I go through that with you. But if you come to the GitHub repo associated with this, of course, go to RWA creator, we go to functions, you go to sources, sell Tesla and send USDC. This is kind of the script that we have set up. Essentially, we're going to be doing these 3 steps here. Our Chainlink functions will sell Tesla on Alpaca for USD. Then it'll buy the crypto token USDC. Yes, you can do this all on Alpaca with the USD that we just got from selling Tesla. Then we're going to send the USDC to our smart contract for withdrawal, right? And so we have some hard-coded things in here to make it a little bit easier. For example, this RWA contract would need to be swapped out for whatever you have. And there's kind of a lot in here. Why is there so much in here? Well, there's a lot of functions that we have to do. We have to first sell the Tesla for USD. We have to place the order. If it doesn't fulfill, we have to cancel it. And if it fails, there might be an issue. We have to buy USDC with USD, and there's a whole bunch of stuff in there. So I tried to make this as modular as possible. So if you want to come in and mess with it and do whatever you want, you can. But this is essentially what the code base is going to look like when it's finished. Go for it. If you want, and if you want to give this a whirl writing this yourself, go for it. We're not going to write this in the video because, like I said, it's kind of a lot. So we're actually just going to simulate the minting. However, the redemptions, that's the script that would get to work. So cool. And then same as the balance, you're going to need a config and a simulator. We have those both in here as well. There's a config in here. And of course, there's a simulator in here for redemptions. It's pretty much the same, right? Pretty much almost exactly the same, just using the redeem script. Great. Okay. So we've covered a lot here. Now, all we really have to do is 2 things. We need to deploy our D Tesla with all this stuff hooked up, and then we can finally test this out. Like I said, you should always do this locally first before going through all the troubles of doing what I'm doing here. Always test locally, always make your deployments dynamic, never hard code like what I'm doing here, right? I'm hard coding in here. In the Git repo associated with this, if you go to script, deploy D Tesla, you'll even see we created this new type deploy D Tesla struct so that we would avoid the stack too deep and so that we can modularize the deployment, right? With subscription ID, the mint source code, redeem source code, functions router, Dawn ID, Tesla feed, USDC, redemption coin, etc., right? You want to always modularize your deployments, and this actually makes it easier to test as well. But for this demo, we're going to forego all that because this is a video. So code base, follow the code base for a better understanding of what's going on. But don't worry, we're inches from actually seeing this live. Very exciting. Let's keep going. So now we want to deploy D Tesla s.sol. This is going to be our deployment script here. And if you're here, you've hopefully gone through Cypher and Updraft, and this is going to be no problem for you because you've done this 100 times, 0.8.25. This should be muscle memory at this point. Contract, deploy, D, Tesla is script, right? Import script from forge std/script.sol. Great, looking good. What else do we want to import? D Tesla, of course, from /src/d tesla.sol. This is what we're going to deploy. Now, if we go to our contract, D Tesla, what are the constructor? Mint source, sub-ID, redeem source. So we don't really care about the redeem source. We can just pass a blank for now. So we can say D Tesla equals new D Tesla, or wait, sorry, Tesla. Sorry, first we need to function run public this. And normally I say you should never do this like so, because it makes testing really hard, but we're also gonna do vm.start broadcast, vm.stop broadcast. This makes testing hard. Don't do it like this. Check the GitHub repo, because what we do in the GitHub repo is much better. Oh, sorry, this should be the other way around. Okay, so this takes a mint source, so we're gonna have to get that. So we'll do string constant alpaca mint source equals /functions/sources/alpaca balance.js. For the redeem, we'll just do string constant alpaca redeem source. For now, I'm just going to say it's blank. And then what we're going to do is in our foundry.toml, we're going to have to give it read access to that. So we'll do fs_permissions equals access equals read comma path equals /. Oops, what just happened? Like this, okay. And then we do a little string memory mint source equals vm.read file alpaca mint source. And I'm just going to pass this straight up. And we're going to say mint source, we need a sub ID, which we're going to do in a second. And redeem source is going to be blank. So we just need a sub ID to get this going, and then we're pretty much good. So let's finally go back to the Chainlink docs. We're going to go to the getting started, and we're going to go to not the functions playground. We want to open up our functions app here, functions.chain.link. We're going to go ahead and create a subscription now. We want to connect our wallet, whatever wallet you want to use. I'm going to be using Sepolia here, and we're going to add an email address and everything. And we're going to click create subscription. And this is going to have a couple of steps here. MetaMask is going to come up. You do need some Sepolia ETH to run this. We're going to create a subscription, wait for our transaction to go through. We're going to sign this as well. And then we're going to go ahead and add funds. We need to add some link to this. We can actually go ahead and get test link in the faucets.chain.link/Sepolia. Go ahead and connect our wallet to this app as well. Let's get 25 test link. Yes, I'm a human being. Give me the link, please. Have to wait here. Wait for confirmation. Request complete. Okay, great. So now I have some test link. I'll add 10 or 15 to my wallet balance here. That's probably way overkill, but if I want to test this a couple of times, we can. Do a lot of waiting here. You could also script this out, of course, but I'm just going to use the UI because we've written a lot of code already. So we're just going to go ahead and use the UI here. And of course, using the UI requires a little bit of waiting. And we're done. Then the next thing we would do is add a consumer, and we're going to do that later because we haven't deployed our code base. We just need our subscription ID, which is going to be this right here, which I'm going to grab now. and pop it into my code base, uint56 constant sub ID equals boom. And oh my goodness, we finally have it. Oh, this is a uint64. Excuse me. We'll just do a quick console2.log address dTesla. Import that as well. Import console2 from forge std / console2.sol. Now, an important note here, we have a couple of issues in our code base. I know, crazy. I made some issues. Who would have guessed? So we're going to deploy this. You're going to see me run to these issues, and I wanted to show you these issues because I wanted to show what the debugging of Chainlink Functions looks like. Then we're going to come back. We're going to fix a bunch of things. We're going to redeploy again, run it again, and boom. Then it's actually going to work the second time. So if you're following along, don't deploy right now. Wait till the end for us to actually deploy. And then also, if you're following along, you really should modularize everything. But in any case, here we go. Okay, moment of truth here. So now all we have to do is deploy this, verify this, and we can actually test out making a call to our Chainlink functions. And if this is successful, we should get a response where our portfolio balance, our S portfolio balance is updated from 0. So if we scroll down, we have a getter function, right? We have get portfolio balance that we can call. And we should get minted some dTesla tokens, right? Because there's going to be plenty of collateral in our account, right? In our, Tesla's going down. There's going to be plenty of collateral in our brokerage account here. So we should be able to mint the dTesla token and have our tokenized RWA. So let's go ahead and do this. I'm going to open up. I'm going to create a new file in here. Include.env. We'll do .phony deploy, and then we'll just do deploy, and we'll get our deploy script here, which is going to be forge script script slash, what's the name? Deploy dTesla .s.sol -- sender is going to be my private key or my address here. Boom, sender. I have already imported my wallets with cast wallet import because they're encrypted, of course. I could also do, instead of -- sender, -- account, I think it's default key. I think that's what I called my testing keys. If you don't have them encrypted, you can of course do -- private key and then pass in your private key like so, but don't do that because that's silly. You should always encrypt your private keys anytime you're working with them. So we're gonna do -- sender, -- account, default key. And then when we actually run this, we're gonna do -- verify, -- broadcast like this, but we're not going to do that. We're just going to simulate this real quick just to make sure it works. So I'm going to run make deploy, count default key. It says script ends successfully. It says it went ahead and passed. If you wish to simulate transaction, pass an RPC URL. Oh yeah. And then of course we're going to have to do -- RPC URL. Mine's set as my RPC URL. We'll do an @ sign here too. And then you're gonna have to do -- etherscan API key. If you're verifying, mine is gonna be etherscan API key, like so. Let me just run this again. Cool, this little @ sign hides the RPC URL and key from the terminal. Okay, simulation complete. This is the chain, this is the gas price, blah, blah, blah. This looks pretty good. Let's go ahead and actually finally do -- verify -- broadcast to actually send it. Here we go. Let's see if this works. Fingers crossed. Okay, enter key store password. This is where I need to enter my password to decrypt my key. Thank you, Foundry, for adding this feature so that I don't have to actually pass my private key. It's always encrypted. And we're running into an error. It looks like we're running into a bit of a gas issue with the deployments. So we're actually gonna go ahead and set this up into 2 transactions. Normally you'd want to have like an initialization here, but we're gonna say function set mint source string memory mint source code external only owner. And then we're just gonna say s mint source code equals mint source code, like that. And then in our deploy script, we're gonna get rid of this line, and we're just gonna say d tesla dot set mint source to this mint source, like this. Fixed it. I needed to set the priority gas price. Looks like setting it to 1 worked. Okay, well, that was all I had to do. Set the priority gas price. Might make this an issue on Foundry or Stack Exchange. Well, in any case, it's going through. Huzzah. And it's been deployed. We're submitting verification. Looks like both of our transactions have gone through the contract creation and then also us adding the source. Okay, great. Let's go check it out. Nice. And it has been verified. Okay, cool. So now that it's up, if we go to read the contract, we go down to get portfolio balance. Where is it? Get portfolio balance. It should be 0 because we haven't sent the request yet. But now what we can do is we can look at our subscription here, right? So let's look at our subscription. We can now add a consumer to this, add consumer. And this is going to be our contract address here. Paste it in, add consumer. We will go ahead and approve it here. All right, cool. Now that the consumer has been added, we now can have a little history here. And when we send this request, okay, we're going to make this API call. We're going to, on this contract, we're going to go ahead and connect to Web3. We're going to call on our write contract functions, send mint request. What this is going to do is going to kick off a Chainlink Functions call, which is going to call our Alpaca account, get the balance, figure out how much, wow, we're really tanking right now. Figure out how much Tesla is in our account. If there's enough Tesla, it's going to mint us some D-Tesla, and we have officially received a tokenized real world asset using Chainlink Functions. Okay, you ready? I am. Let's go ahead. Let's connect our wallet. We're going to go ahead and request 1 Tesla. So we're going to put 1 in here. We're going to put 18 zeros on it because that's what we want to do. We're going to select write. MetaMask is going to pop up. Here we go. We're going to go ahead and confirm. View the transaction. Transaction's now in flight. Go to our functions history here. We'll do a little refresh. Once this transaction goes through, our functions will pick up this transaction. Okay, this transaction's gone through. We'll look at Chainlink Functions. We have a pending transaction. So it's calling our Alpaca API right now. It's in queue. We've successfully called Chainlink Functions. And we actually ran into an error, but we can actually go check out the status of these here. Cannot read properties undefined, reading portfolio value. And one frequent reason for failure is too much gas being used. Type error, cannot read properties of undefined, reading portfolio values. And this is where having really good errors is actually really important, right? Because right now it's kind of difficult for us to know, we just got this error reading portfolio value. So since we got this, and I know what the issue was, we didn't actually export our environment variables, and we didn't actually tell our Chainlink Functions the correct secrets version, we're going to have to go and fix that. And the other thing is, so I'm not going to show you fiddling with this, but right now there is a max callback gas set for Chainlink Functions. So if you're playing around with this and you run into callback issues, definitely be sure to go submit something on the Chainlink Functions saying, hey, we want to be able to spend more gas, because that's definitely one of the issues that currently happens. And I'm actually going to skip over running into that, and we're going to modify our code base to not have to deal with that. But in our code base, if you remember, in our source here, we have our secrets, and we uploaded our secrets, obviously with our upload script. However, we actually didn't connect our dtesla.sol to the secrets, right? So we sent the request, but there was no way for Chainlink Functions to know which secrets it's supposed to use for this request. So we actually have to update this request and redeploy with the correct secrets here. So we can actually find an example like this. If we go back to the Chainlink documentation using Dawn hosted secrets, we can open this in Remix and we'll get an example contract that actually works with a Dawn hosted secret. So if you scroll down in here, there's a couple more things that we needed to add here. If we look into their send request, we need encrypted secrets URL, Dawn hosted secrets slot ID, Dawn hosted secrets version, and that's pretty much it. So we need to add these to our contract. And then we'll just add it to our rec here. So, whoops, we can go back to here now. And we're going to do a couple of things. So let's actually redeploy with this, because we just learned it was a priority fee issue. But I'll leave this in here anyways. And then what we're going to want to add is these three things, which I'm going to hard code for now. So up in the storage variables, paste these in, bytes encrypted secrets. Now we don't need an encrypted secrets URL because we're using one of the public gateways. So these are the only two that we need. Just the Dawn hosted secrets slot and the Dawn hosted secrets version. And when we ran our upload script, we were actually given both of these. So if I go back to the package.json, we can actually just run this again, npm run upload secrets. Ta-da, here's our secret version, and the slot we set, slot was 0. So we can go ahead and roll with that. So I'm gonna hard code it, but maybe it's a good idea to not do that or have some type of setter function here. So I already forgot what the slot was. Slot is 0, okay. So so these need to be reversed. And this is a 64, and this one is an 8. So the secrets slot is going to be 0, and then the version is going to be this number here. Like I said, it probably would be a good idea for us to write like a setter, kind of like we did with mints or set mint source, but I'm going to skip it for now. And we're going to scroll down, and in here, we're going to want to update this. So before we actually send it, we're going to do rec.add Dawn hosted secrets, and then we're just going to do the secret slot and then the secrets version. Thank you, GitHub Copilot. Now the final thing that we're going to run into doing this is that I'm kind of cheating a lot here. Like I said, the callback gas is actually a lot lower, and this whole bit here won't work great. So I'm going to cheat a little bit, and what we're going to do is we're going to separate this. So we're going to actually let me cheat like this. We're going to separate this. I'm just going to comment out this whole section, and our mint fulfill request, all this is really doing is updating our portfolio balance and then allowing somebody to call mint. So what we can do is we can have the fulfillment for now just update the balance. So we're kind of hard coding this. If we wanted to send this to production, which Chainlink Functions is in beta right now still, so we wouldn't send this to production anyways. But if we wanted to send this to production, we would just have to have 2 separate contracts with 2 separate fulfill requests, right? That's how we would basically get around this gas issue here. Because doing this conditional is kind of a lot of gas, and we want to just use as little gas as possible. But we can have this function called finish mint, where external only owner, where we can just say, or we can use this request ID. We'll save it as a storage variable. So up here, we'll do bytes 32 private s most recent request ID. When we call the redeem request, we're also going to say s most recent request ID equals request ID, and we'll put this tracker in here, send mint request most recent request ID equals request ID like this. And then when we call, and what I'm going to do is I'm actually going to copy this, and I'm going to cheat a little bit for this demo. I'm just going to call this the mint function here. We're actually not even going to do that. S underscore most recent request ID, and then amount of tokens to mint equals S request ID to request. We're just going to kind of cheat a little bit here. So For production, we would obviously want to kind of flesh this out a little bit more, but for this demo here, we're going to just make it nice and easy so that we can finally arrive at finishing minting here and getting our tokenized bits. So we went back and we cleaned up a couple things. I know there's a lot of code here, but we added in the Dawn secret slot and secrets version. We added that down here in our send mint request. This way, we'll avoid getting this error. Additionally, in our .env, we added the export so that these secret keys and API keys are actually working. I decided I didn't want to put you through the pain of dealing with the gas issues that you'll run into. So we just made our fulfill request super, super quick, just like this. S portfolio balance equals whatever the response is. So we update the portfolio balance and then we go ahead, we finish minting like this. We probably would do a little check here where if the portfolio balance, actually, let's go ahead and copy paste that because that's good to have anyways. Right here, we are going to copy this down in finish mint because I think this is important enough to do. If the collateral adjusted ratio is not good enough, we'll revert. We don't have enough collateral. Otherwise, we'll go ahead and mint. So, and then our script, we're going to want to make sure to multiply by 18 decimal places as well, so that we make sure to have 18 decimal places. Now, true moment of truth. Looking at the makefile, forward script deploy, everything looks good. RPC, verify broadcast. Let's look at our deploy script. Oh, we want to add the mint source in here. Looks like I messed with this. I was playing around. We're going to add the mint source sub-ID alpaca redeem into our script. Let's actually run this makefile without verify broadcast real quick. Let's just see if this make deploy works. This will compile everything, make sure everything's looking good. Yeah, unused function parameter, fine, whatever. Okay, cool. Let's go ahead and ship this and we'll actually see ourselves, mint ourselves some D-Tesla. And we'll just wait for a little bit. All right, it's gone through. We can now go check it out on Etherscan. Cool, we're gonna copy the address, come back to our functions now, go to our same subscription. We're gonna make sure we're connected here. Add a consumer, paste it in. Now that the consumer has been added, we can finally go to the D-Tesla contract. And what we're gonna do here in the right contract, I'm gonna connect real quick, boom, connect to MetaMask. What we're going to do is we're going to call send mint request. And what this is going to do is on our smart contract. Okay, here's what's going to happen. D-Tesla. It's going to send mint request, which is going to kick off a request to our JavaScript code, which we wrote. Alpaca balance, which is going to check our alpaca balance for how much Tesla we've purchased in our portfolio. It's going to go through a Chainlink Functions that we just set up. And the Chainlink oracles are going to decrypt our secrets using threshold signatures, which is kind of insane. And then what's going to happen is once it gets the answer, it's going to return the data back to our smart contract with mint fulfill request. Well, not really. We're kind of cheating a little bit because this demo has already been super long. We're going to go to the fulfill request, which is going to update our portfolio balance, which is just going to update our portfolio balance. And then we're going to call finish mint, which using that portfolio balance, if it's enough, we're going to be able to mint the D tokens to ourselves. You ready? Because I sure am. Let's go. Let's do this. Let's zoom in a hair. Boom. Add some zeros. 118. Add. Write. MetaMask pops up. Confirm. View the transaction. Once this finishes going through, we're going to check out our Chainlink Functions GitHub UI. Looks like it's gone through. Let's go check Chainlink Functions. We'll give this a little refresh and we'll reconnect. We scroll down. We have a pending transaction. Exciting. We'll give another little refresh. We'll scroll down. Oh, looks like we have a fulfillment. Let's go even look at it. Looks like the computation was a success. We have an output here. Let's look at our Alpaca dashboard. Wow, we're super down on Tesla. That's fine. Looks like the callback was successful. So let's go back to our contract here. Let's go read the contract. Let's look at that portfolio balance. Where is it? Where is it? Where is it? Get portfolio balance. Boom. we have a portfolio balance. Okay, so let's finalize this. Let's finish minting ourselves the D token based off of our new portfolio balance. So now, finally, when we hit finish mint, confirm, once our transaction goes through, we'll be able to take our balance, the owner's address, go to read contract, reconnect, go to balance of, paste it in, and we do indeed see we now own some RWA. We can also take this token, pop it into our MetaMask, D-Tesla, import. I now have one beautiful D-Tesla in my MetaMask. Now that was one of the two ways to make tokenized real world assets. The other way is the synthetic method, which if you've been through the Cypher and Updraft curriculum, that method is actually trivial. And you can actually go through the RWAs creator repo to actually learn how to build those yourself. But now you've learned a ton more about tokenized RWAs and how to build your own tokenized RWAs with real off-chain collateral, with real things in the real world. Now remember, Chainlink Functions is in beta right now. There's a couple of tweaks that they're looking to make to get it production ready. Use it at your own risk. However, maybe you'll be one of the first people to use Chainlink Functions to make some really, really powerful tokenized real world assets and use the methodology that we taught you here. So that's it for me. Thanks so much, and we'll see you next time.